day, everyone. My name is John Paulo B. Broas, and my thesis partner is RUDOLF Christian Ogitan. Our thesis advisor is MENANDRO MARQUEZ, and we will be presenting our topic, low temperature synthesis of manganese-doped zinc oxide while by a wet chemical precipitation approach.
Zinc oxide. It is a N-type semiconductor that is used as an additive in numerous materials and products like sunscreens, piezoelectric sensors, gas sensors, UV detectors. All these are possible due to zinc oxide's optical properties, which are its wide band gap and its blue-chip absorption capacity, which lets devices with zinc oxide to work at much higher temperatures, voltages, and frequencies, while at the same time absorbing ultraviolet light in the blue spectrum. Next slide, please.
Now, traditionally, synthesizing using wet chemistry method, which involve first generating the particles in a solution, drop casting the wet particles into a substrate, and removing the solvent and other materials from the particle. This wet synthesis method requires a significant amount of time and chemicals. Wet chemical synthesis has emerged as the most promising route towards high yield and mass production of such materials. These materials are now finding increasing application in a wide range of areas, including catalysts, energy production, storage, and sensors.
Doping. It is the technique used to change the properties of materials by changing the number of electrons and holes. There are two known types of doping, p-type doping and n-type doping. P-type doping adds atoms that create vacancies or holes, which are the majority carriers, while n-type doping is where the majority carriers are the ones that adds extra electrons called donor atoms. One example of n-type doping is zinc oxide. This is because of its oxygen vacancies occurring in intervening spaces which are occupied by zinc ions. In our research, we use wet chemical approach to dope zinc oxide because of advantages such as ease of use, it's cheap and can be done in a wide range of environments from laboratories to houses like we do, using only the minimum of materials. Next slide, please. Manganese as dopant. Zinc oxide suffers from fast recombination of electron pairs, which leads to a reduction in its photocatalytic efficiency. Thus, to improve zinc oxide properties, for our research, we use manganese because, according to one of our references, transition metals increases the surface defects and optical properties of zinc oxide. Next slide, please.
Now, for the motivation of the study. Doping zinc oxide with manganese can be done by different methods such as RF magnetron sputtering, molecular beam epitaxy, salt gel method, and hydrothermal method. Among these methods, salt gel and hydrothermal methods are among the most attractive options because they can be carried out at room temperature, produce high purity level, and generally low cost. However, literatures regarding manganese doping of zinc oxide prepared by a wet chemical precipitation approach are very limited. Thus, in this study in particular focuses on incorporation of manganese as to zinc oxide using wet chemical precipitation approach without using a furnace or high temperature annealing. Now, for the significance of the study, this study shows that pristine zinc oxide and manganese-doped zinc oxide can be prepared without using energy-intensive equipment and apparatus. It also opens the possibility of synthesizing and doping other metal oxide using wet chemical precipitation. This study also contributes to the body of knowledge of understanding the effect of optical and structure of manganese-doped zinc oxide, which could lead to the development materials applicable to different fields of study. Now, for the objective of the study, the general objective of the study is to synthesize manganese-doped zinc oxide via wet chemical approach. Specifically, it aims to determine the crystallinity of the sample using XRD, verify the incorporation of manganese in zinc oxide via EDX, observe the optical absorption of doped and non-doped samples using UVBs, approximate the optical band gap, and measure the particle size using dynamic light scattering technique. Now for the scope and delimitation, in this study, a device prototype will not be made. Characterization, chemicals, and treatments are limited to those cited under the methodology section. Now, for the methodology, the first solution, zinc oxide, is combined with ethanol. For the second solution, manganese chloride is combined with ethanol. And for the third solution, NaOH is combined with ethanol. Then we will heat all the solution to 50 degrees. We will combine solution 1 and solution 2 into a bigger beaker, the solution 4. Solution 4 needs to be stirred for 30 minutes in 80 degrees. Then dropwise add solution 3 into solution 4, the solution 5. Solution 5 will now be on magnetic stirrer for 2 hours with a maintaining heat of 60 to 65 degrees. Afterwards, it will become a paste-like sample and wash it with distilled water. Then we will cool the solution into room temperature, then calcinate the solution in a microwave with low heat in 5 minutes. Then we will store the solution into a Boston amber glass for sampling and testing. Now, zinc chloride and manganese chloride act as a precursor, and absolute ethanol was used as a solvent to synthesize manganese-doped zinc oxide. So basically, the synthesis of electrostatically stable manganese-doped zinc oxide was performed in an alcohol solution in order to avoid formation of zinc hydroxide. This equation over here shows how the zinc oxide was formed from the chemicals provided.
The high amount of zinc and oxygen in our zinc oxide sample, as seen in the pictures far south, shows that we have successfully created zinc oxide. In the doped particles, we can see the color signature results that manganese is seen near zinc oxide and oxygen, which proves that we successfully incorporate manganese in zinc oxide. In our research, we found the type and style of doping, which is N-type doping and substitution doping, respectively. One of our references revealed that N-type doping happened because manganese having lots of electrons, making the electrons the majority carrier, while substitution doping happened because manganese ions replaced some zinc ions to form manganese-doped zinc oxide. Next slide. In our UVV's results, it yielded two fascinating results. One is increasing manganese concentration increasingly shift the absorption ability of manganese-doped zinc oxide particles to the blue spectrum. According to one of our references, this is due to the strong exchange interaction in the short-range skin system and excess impurities on the surface, which manganese is responsible for. The second fascinating result is the band becomes wider as the more manganese is added. This trend is seen on the synthesis material that has 1, 3, and 5% concentration of manganese. The reason our band gap is higher than similar papers is because we use low temperature, which according to one of our references says that band gap is affected by annealing or calcinated temperatures.
Now for the result of our DLS for undoped sample, which obtained at 25 degrees with scattering angle of 173 degrees, shows a Z average of 6,687.7 nanometers. This result proves the direct agglomeration of particles happening in the sample and explain the band gap result found in our analysis of UVBs. Since Pi is greater than 0.7, this indicates that the sample has a broad size distribution. Now for the dope sample of 1%, 3%, and 5% manganese dope zinc oxide obtained at 25 degrees with a scattering angle of 173 degrees shows a Z average of 4,450.5 nanometers, 3,318.8 nanometers, and 8,631.9 nanometers. This result also proves that the direct agglomeration of particles happened, which helped prove the band gap found in UV-Vis analysis. Since the PA is less than 0.7 in 1% to 3% sample, it has a narrow size distribution. But since in our 5% sample, the PA is greater than 0.7, it has a broad size distribution. It is evident that the average found in 5% sample is the biggest in all the samples.
Our XRD analysis of the 5% manganese doped zinc oxide yielded three results: the crystallite structure, the crystallite size, and the lattice parameter. The crystallite structure of zinc oxide was found through the use of the XRD analysis program FALL-X, and the structure found is the hexagonal word-side structure. We found this out by matching the peaks of our synthesis material with the peaks of zinc oxide from the database of QualX. Then while sorting through the QualX database, we noticed that our peaks matches those with zinc oxide peaks with Miller indices that was identified as having a hexagonal word-side structure, which confirms that our 5% manganese has that said structure. And the other result we found is the crystallite size, which is 7.96 nanometer, which we found using the free-to-use XRD analysis tool FitYK. Using this tool, we were able to determine the data needed to use Scherer equation to find the crystallite size. And the last result is the lattice parameter, which was found using Bragg's law. And the result we found for constants A and C are for A, 3.19 Armstrong, and C, 5.22 Armstrong. Next slide, please. The type of doping that happened in our research is called substitution doping, which is represented by this illustration. It is where manganese ions replace zinc ions in some places, doping it and enhancing the properties of the doped material. Next slide, please. So in conclusion, the XRD, we identified that the sample has a hexagonal quartz crystal structure. It has an average crystal size of 7.6 nanometers, and we were successful in obtaining manganese doped zinc oxide. And via EDX, we verified the incorporation of manganese in zinc oxide. While in the UV-Vis, we showed the increasing trend in band gap, indicating a progressive increase in band gap with increasing manganese concentration. And for the DLS, we showed that for pure and 5%, it has a broad size distribution, while 1 and 3% has a narrow size distribution.
Now, for our recommendation, high doping concentration can be done. Other optical characterization may be done for this material to be used in a good optoelectronic device. For the application that calls that for high purity zinc oxide, we recommend calcination. That's all. Thank you.